So cool. Bo, thank you so much for joining us today. I'm really excited about this. I sort of stumbled across your paper while trying to learn more about some of the mathier sides of machine learning. I'm not an ML person myself, but I have a math background. And so when I try to learn about a topic, that's often where I start. And I think this is a really interesting research topic. So I'm excited you're able to come to us today. So with that, I'll give you the floor. And yeah, thank you again.
Thank you, Max. I'll present the paper Symmetries, Finite Minima, and the Conserved Quantities of Gradient Flow. This is a joint work with Eldon Ganef at Redmond University, also with Robin Waters, who is a professor at Northeastern, and my advisor, Rose, and also Nima Dekmami at IBM Research. Okay. To give a quick background or motivation of this paper, there has been some paper that noticed that the minimum of neural networks is connected through Mongoose valleys instead of being isolated points. But very little is known about the origin of these valleys or their parametrizations. So this leads to some open questions, such as like what are the structures of this minimum? And other questions such as, is there a way we can move along these minimums so that the loss is not changed? This leads to the concept of symmetry, which is transformations that leaves something unchanged. So in this case, we want to travel on the level set of the loss function, in this case, the minimum, so that we don't change the loss. So here's the outline of my talk. So I'll start from definitions of symmetries and group actions. And after that, I'll give the formal definition of parameter space symmetry. We'll show that most of this symmetry comes from the equivariance of the activation function. We also present a set of new nonlinear and data-dependent symmetries. And the final thing in that part would be, we'll show that we'll derive the dimension of the orbits of this symmetry, which is a lower bound of the dimension of the minimum. And for the second part, I'll talk about a concept called conserved quantities in the gradient flow. We'll show that it's often associated with symmetries or infinitesimal symmetries. And finally, I'll talk about some applications of conserved quantities and parameter space symmetries. So a high-level idea for symmetry is that it's a transformation that leaves certain properties unchanged. A familiar example would be symmetry in data. So for example, if I rotate a picture of a cabinet, it's still a cabinet. So the transformation here is the rotation of the image, and the invariance is that the label does not change. A second example of symmetry, which is the symmetry that we're more interested in, is symmetry in functions. So consider this very simple example function f. So here f takes in two matrices and outputs the product of those two matrices. And we notice that if we transform u and v into u g inverse and gv, then their product will not change. So here the transformation is done on the parameter space of a function, and the function's value, we want the function value to be invariant. To describe these symmetries in a more formal way, we need the language of groups. A group is a set together with a law of composition. The binary composition needs to be associative, and the set needs to have an identity and an inverse for every element. A recurring example in our paper is a general linear group, which is denoted as this GLR. It's a set of H by H invertible matrices with real entries. So here's a composition is the matrix multiplication, which is clearly associative. And the identity element is the identity matrix, and the inverse is just the inverse of matrices. And once we have a group, we can define how a group acts on a space. So an action of a G on a space W is a function that takes an element in the group and a point in W, and it outputs another point in W, which is like the transformed points by the group element. The action is to satisfy these two rules, the unit axiom and multiplication axiom, which is another form of the associative law.
And Bo, for groups, does the inverse have to be unique?
Yes.
Okay. Sorry, it's been like 5 years since I learned this, so I don't remember off the top of my head.
Sure. So it needs to have a left inverse and a right inverse, and they need to be equal. So now we're ready to introduce parameter space symmetry. Well, actually, before that, we need to get some concepts about the parameter space, which is, so in our paper, we consider parameter space to be a vector space. It's possible that it can be another more complicated object or space. So for now, we consider everything to be a vector space. So in the setting of machine learning, there's usually a data set. The X are often called data, and the Y are often called the labels of the data. And once we have a data set, we can define a loss function, L, that maps from the parameter space to a real number. So we usually have a neural network called, so here we call that the function f theta. F takes each data point and outputs a label for that data point. And the output of f usually maps is usually the same as the dimension of the labels y. And then we also need a cost function, which roughly measures how close or how far the predicted label is to the actual label y. And the loss function is the sum of the of all the cost for all the data points. And the objective is usually to minimize the loss. So that's the objective of neural network training. And parameter space symmetry is an action of a group on the parameter space that leaves the loss invariant. In other words, if we have a point in the parameter space that's called theta, then if we transform theta by a group element, the loss should not change. In this case, we also proved, and I think it's already known that if theta star is a local minimum, then so is G dot theta star. I think this assumes that the group action is linear. But this gives us a way to construct.
Sorry.
At this
so
part
local minimum. Yeah. So local minimum in the sense of loss function.
Yes, in the sense of the loss function L.
Well,
and
sorry. So then theta star is equal to the loss function for theta star is equal to the loss function evaluated on G theta star. Isn't like this the final part obvious?
So to show that G dot theta star is also a local minimum, or more generally a critical point, we need to show that its derivative or gradient is also 0. So the proof is indeed straightforward, but the previous the definition for symmetry just requires that the loss value at those 2 points are equal. The final statement requires that their gradient are equal, and both needs to be 0.
Oh, cool. Thanks for clarifying.
Thanks for the question. So this gives us a way to like carve out or construct this minimum in the way that we can move in the orbit of this group action. So we can transform theta by different g's, and we arrive at different points of the minimum. Yeah. So and then we'll talk about another concept called the equivariance of the activation. So to consider a simple example, let's consider a 2-layer neural network. Here the parameters are 2 matrices U and V, and they are often called the weights of the 2 layers of the neural network. And X here is the input, it's like the data. So the output here, U sigma of Vx, is the output of a neural network and is going to be compared against the label. But for now, we are only interested in structure of this neural network. Here, sigma is it's an activation. It's called an activation function. It's often taken to be an element-wise function, but it doesn't have to be. So as we showed, there's a symmetry on the parameter space of this function. We can transform U and V into UG inverse and GV so that the output of the neural network will not change. And what we observed is that suppose we have a G that's a symmetry group, and we have a representation pi of the group. Then suppose also that the following relation holds. In other words, sigma GZ equals to G times sigma Z. So this is kind of saying that sigma and G are commutative. So if this is all true, then we have this equation, sigma U times sigma of Vx equals to U times G inverse and sigma GVx. And then we can define the following group action, which is a symmetry. So the way to verify this is just to multiply them together and verify that it equals to U sigma V. So the relation that sigma and G commutes is often called an equivariant of the activation function. So we find that this is an easy way to construct these parameter space symmetries. So the upshot here is that these symmetries are often related to equivariance of the activation function. So the previous activation functions are often restricted to be like identity function or rangle. And the symmetry group that allows this equivariance to happen is often quite restricted. When sigma is an identity function, this group G can be taken to be all of general linear group or all of invertible matrices. But when sigma is, for example, the rangle function, which is it limits the symmetry group to the only group of positive scaling group. So we also find a group action that can be applied to the entire general linear group regardless of the activation function. So this action is kind of different from the common ones we learn about in algebra classes in that it's not linear and also it depends on data. So usually the action just takes a group and a point in the parameter space. But here we also takes in the additional input, which is the input data X. We have the complete form of this action in our paper, but for now, the R matrices are a kind of orthogonal matrices that's defined by the spherical coordinates of X of Vx or GVx. And we find that transforming U and V in this way will not change the output of U sigma Vx. There are some pitfalls of these actions in that so this only holds if X is a vector. In other words, this transformation only leaves the loss invariant on one single data point. This is apparently not very useful. So in our experiments, we use a different set of transformations. I put the symmetry in quotations here because it's not exactly a symmetry in that it does not really satisfy the unit axiom and the transitive property of the group action. Nevertheless, it approximately preserves the loss. So it's like an approximation of the equation 2 shown here. And for the final result of this part, I want to talk something about whether we can find a lower bound for the dimension of the finite minimum using what we know about symmetry. So again, we consider the two-layer case. And so an orbit is the set of points that can be reached by applying a group action. So in other words, the orbit dimension is sort of like a lower bound for the dimension of the minimum. And this table shows the orbit dimension of different symmetry groups corresponding to different activation functions. And the way we calculate these dimensions is by first find the dimension of the stabilizer of the group. The stabilizer would be the set of points that doesn't change that doesn't change the parameters. So and then the orbit dimension is equal to the dimension of the group minus the dimension of the stabilizer. So when the activation function is the identity, which gives us the linear neural networks, symmetry group is the entire general linear group, and the dimension of the symmetry group is h squared. So when the hidden dimension h, so the dimension between the two matrices is small, we get the orbit dimension to be the entire group dimension. But when the hidden dimension is larger than the input and output dimensions n and m, then there's a non-trivial stabilizer. So there's correspondingly a smaller orbit dimension. And we derive similar things for a couple of different activation functions. The first one is homogeneous activations. So these are activations that that allows for a rescaling symmetry. So you can scale the input or scale the v by some positive number, and then the sigma vx will be scaled by the same number. So in short, the symmetry group is a positive rescaling group, which is a set of matrices that has positive diagonal entries and zero everywhere else. The group dimension here is h, and again, the orbit dimensions is either h or a smaller number that is n or m. And for the radial rescaling group, a radial scaling activation, it has a orthogonal symmetry. And the corresponding orbit dimension is h chosen 2, which is also the dimension of the orthogonal group, or something smaller. So other questions so far?
I'm curious about what you can actually calculate on like a real learned neural network. I guess I understand the group theory, but I don't have any conception of what this looks like when you go and run some big cluster and learn some representation of some data. So I don't know if you're going to get to that later in the presentation or not, but if not, I'd be curious to just hear some insight about that.
Yeah. So other than the so if the activation is not identity, if it's okay, so we'll only talk about cases listed here. So for a two-layer neural network, we already have the form of neural network. But for a deeper neural network, we need to account for these symmetries between every pair of consecutive layers. And then once we have that, then the symmetry group would be the product group of a number of general linear groups, and then we'll compute the orbit dimension of each one of them. But that's an interesting question. I think this result we have is limited to a two-layer case.
But it sounds like the complexity of the calculation is only linear in the number of layers, right? So yes, it's not that bad.
That's true.
Yeah. Cool. Okay. Very cool.
So for the next part, I'll introduce a new concept called conserved quantities and show that it's somehow associated with these parameter space symmetries. A gradient flow is a continuous version of gradient descent, which is a common way of training the neural network. So it has this form. is a curve that moves in the direction of the opposite of the gradient. Remember that in neural networks, our objective is often to make the loss as small as possible. So to minimize that function, one natural way to do that is to move in the negative gradient direction. So in training, we usually use a discretized version of this called gradient descent. But here we only focus on the continuous version for the theory part. A conserved quantity is a function or is some quantity that doesn't change along a gradient flow trajectory. So theta here is the parameters, and theta s and theta t are the value of parameters at two different times along the gradient flow trajectory. So if q is conserved, then the q at all time should be the same. In other words, the time derivative of q is 0. And in the paper, we show that the parameter space symmetries leads to conserved quantities via the infinitesimal action. So the infinitesimal action is roughly a very small group action. So the proposition is like, suppose the action is linear and leaves the loss invariant. In other words, it's a symmetry. Then for any m in the Lie algebra of the group, there's a conserved quantity given by this inner product of theta and m acting on theta. So this is a table that summarizes what these conserved quantities or conservation laws looks like. So the left column is a general case. If m is any element in the Lie algebra, then we get the differential equation. So theta here is the vectorized parameters, m is a matrix. Theta dot is also taken to be a vector. When m is a symmetric matrix, we can integrate this theta dot m theta to get the conserved quantity. But when m is anti-symmetric, this conserved quantity will always evaluate to 0. So it's not very informative. But in that case, we can rewrite that differential equation so that it resembles the conservation of angular momentum. So here in the third column, r and phi are the polar coordinates of theta. So this is like the angular momentum of a two-dimensional subspace of the parameter space, and summed over all those two subspaces. And so one way to see how conserved quantities is useful is that it sort of labels the gradient flow lines. Each gradient flow lines is associated with the value of the conserved quantities, it kind of parameterizes these flow lines of gradient flow. And similarly, it also parameterizes the flat minimum, because moving in the minimum also changes the value of these conserved quantities. So this picture shows a very simple example of a neural network. So here we have the two-layer linear network, and the only parameters are u and v, which are both scalars. You can think of them as 1-by-1 matrices. And here the two green lines are the minimum, and the different colored lines are the gradient flow trajectories. So here we can see that each trajectory corresponds to a different value of conserved quantities, and also they converge to different points on the minimum. So the minimum in this way is parameterized by the conserved quantities. And for the final part, I want to talk about some of the applications of conserved quantities. So in our paper, we ran some experiments to show how conserved quantities are related with convergence rate or generalization. By definition, conserved quantities does not change along a gradient flow trajectory. In gradient descent, is not exactly conserved because of the discretization error, but we show that it's still approximately conserved. So in a two-layer neural network, we show that the convergence rate depends on the value of the conserved quantities. So the conserved quantities kind of labels the different trajectories, and the convergence rate is different on different trajectories. So convergence rate depends on the conserved quantities. We didn't work out the exact relationship between convergence rate and the values of Q, the conserved quantities. But in experiments, we do observe a strong correlation between these two quantities. And similarly, different trajectories converge to different minima, and which has different conserved quantity values. So we can also find a relationship between generalization and conserved quantity values. So here we measure generalization by the sharpness of the minimum or the magnitude of the eigenvalues of the Hessian. And we observe that if we initialize the parameters by different values of Q, then the distributions of the eigenvalues of the Hessian after it converges would be different. And another useful thing about conserved quantities is that since it partially parameterizes the minimum, it can help show that only a small part of the minimum is reachable. So in this experiment, we initialize the parameters using Xavier initialization, which is a common way to initialize neural networks. And we find that the distribution of Q under this initialization is concentrated to be around 100, and that actually depends on the number of parameters. But the point is that the distribution of Q is kind of limited to a small range. In reality, the value of Q can be taken from negative infinity to infinity. So one way to see why common initializations are effective is that it restricts the range of conserved quantities to a small range. So whether this is desirable or not is not clear from this small experiment. But conserved quantities does help to show that the effect of some initializations. So to summarize this talk, we find a general framework for finding continuous symmetries, and these continuous symmetries can be used to travel on the low loss valleys. We also find that these symmetries are often related to the equivariances of the activation. So these equivariances allows us to find symmetries for different architectures. And to make these symmetries more general, we define a set of nonlinear and data-dependent symmetries. And from these symmetries, we can derive conserved quantities in gradient flows, and we show some applications for these conserved quantities. That's the end of my talk. So I will be open for questions. Thank you.
Thank you so much, Bo. That was fantastic. Well, there's a very small group of us here, so I think we can just kind of unmute and ask instead of having to do like an elaborate, hand raising ceremony or something. So if anybody has questions, I think they should just go for it.
So hi, so I actually have some questions. So obviously, I think a lot of us here are not from machine learning background, so some of the motivation of this talk might be a little bit lost, I imagine, for some of us. So I was wondering, like, you mentioned, like, in the first half of the talk, you calculated the dimension of the orbit, and all that seems really cool. But at the end, I see your take-home message is that these kind of symmetries carve out the low loss value, which seems like very significant. But I kind of failed to make that connection of how does these calculation carves out the low loss value.
Yeah. So from a machine learning perspective, our initial motivation is just to understand the structure of the minimum. And since we have these symmetries, the orbit of these symmetries are embedded in the minimum, in a less formal sense. So I don't think it's accurate for us to say that symmetries causes the low-loss values, but it gives us a way to like give this minimum a structure, or at least part of the structure that helps us explain, for example, whether there are ways to move on the minimum, which is interesting to machine learning people. And by the way, there's a recent concept called mode connectivity, which basically says that all the minimum of neural networks are connected. There are several versions of that. Some says that all the minimum are connected linearly up to a permutation. So it's an active topic of research in machine learning, and I think our work is a good way for mathematicians to get started in this area.
I think also some people have tried to use homology to understand this, right? I seem to remember reading some papers that are homological in nature about minima and neural networks.
I'm not familiar about that, but that sounds interesting.
Okay. I don't know if it worked or not. I assume if it did work, you would know about it.
So I also have a question about the second part of the talk. In the second part of the talk, you mentioned like these kind of invariants corresponds to the trace of the descent, right? So like I forgot the exact name. So is this a one-to-one correspondence, and can two trace of the descent leads to the same minimum?
No and yes. So it's definitely not a one-to-one correspondence. So just by looking at this example, so sometimes we call it trajectories. Others have also called it maybe the flow curves, or because it's like the curves in the parameter space. So for example, in this picture, there are two red curves, which corresponds to the same value of conserved quantities, -3. So that means each conserved quantity value can correspond to several different curves. And also, so this also all of these red curves leads to minimum that has the same conserved quantity value. And apparently here it leads to two different values, two different minimums. And in general, I remember saying that the conserved quantities parameterize the minimum. That is not entirely accurate. It's more like a partial parameterization, because the number of conserved quantities we find is usually much smaller than the dimension of the minimum.
Do you have any?
Yeah, sorry.
Sorry, I didn't mean to interrupt you. But I was curious, do you have any insight into how conserved quantities likely evolve layer by layer in a many layer, like a deep neural network?
Yes. So in that case, we would actually have more than one conserved quantities. So just trying to find an example of that layer structure. So here we can extend these two-layer neural networks to more layers by replacing X with another layer. So replacing X with, for example, sigma of WX. So in that case, we would find conserved quantities between every pair of consecutive layers.
So does that give insight into like the relationships between the number of minima in different layers, for example, or the placement of those minima, or things like this? For example, if you look at layer n, do you know something about the minima that will arise in layer n+1?
I usually think of minimum as a global concept. So all the parameters together gives rise to the minimum.
I see.
So,
okay.
Yeah. But yeah, I just think that adding more layers can give us more conserved quantities. But I'm not sure how each new layer would contribute to the change of structure of the minimum. That's an interesting question, though. Could be a future work.
Well, maybe that opens up another question, which is, do you mind telling us a bit about your future work, or whatever you're comfortable sharing? But I'm certainly curious, what's next with a project like this?
Yes. So I'm generally interested in parameter space symmetry. So as a direct extension of this work, we're now working on relating the topology of the group to the topology of the orbits to the topology of the minimum. So it's like, so all of the groups we considered here are D groups, which are continuous. And the group actions we considered are also continuous, which means that the orbits are also continuous. So that gives us a way to somewhat describe for example, the connectivity of the orbits or the minimum. So that's what I'm working on.
Yeah, that sounds very cool. Are you looking at the fundamental groups as well?
Not yet.
Okay.
So we are still working with these gender linear groups.
Gotcha. Okay. Well, that sounds super cool. Well, this is a little bit of a peculiar audience for you, because you have a bunch of people who know nothing about the machine learning but understand all the group theory. And I imagine, correct me if I'm wrong, but probably as a machine learning person, you usually have the opposite, right?
Right.
I would think most machine learning people probably know a bunch of analysis and differential equations, but not so much the algebra.
Yeah. I think that would be an opportunity for mathematicians to introduce these concepts into machine learning and discover something new.
Yeah, definitely. Do we have any other questions?
So actually, sorry, I have another question. It seems like all these groups are generated by the activation function. Am I understanding that correctly? And yeah, so let me think about my question. So the orbit of this group well, if you start from a minimum, and the premise is that the orbit of these groups are all minimas, right?
Yes.
And how much minima do you need to start with? How much minima do you have to find until the orbit give you all the minimas?
That's a good question. I'm also thinking about that right now. So from the result of this paper, we actually don't know about that. So, okay, so what I know is that there is definitely we can definitely define a set of points, and the orbit of all those points would generate the entire minimum. That's actually like a partition problem. But the difficulty in trying to find the exact number of orbits we need is that the minimum does not have a nice structure. So it's difficult to find a way to quotient out anything. In other words, the orbits that consist that together make up this minimum are not. They are very different. They have different dimensions. They have different many different properties. So, but that's a good question, and we're also working on that. We're trying to understand what these different orbits looks like, and maybe how many kinds of orbits there are to construct this minimum. Does that answer your question?
Yes. Sorry,
Oh, thanks.
Though I have a question, and then maybe we'll wrap up because I think we're close to exhausting the amount of algebra questions that we have.
Okay.
But I was just curious, and maybe this is very naive, but is there some relationship between like an accuracy versus precision trade-off and the number of minima that you expect to have? For example, I might imagine that a very precise model would have a more complicated shape to it, right? Because it very precisely matches the data, but then it also it may not generalize that well, again, because this complex shape has more local minima or whatever. But again, I know nothing about machine learning. I'm just kind of making this up, so I don't know.
That's actually a very good intuition. That's one thing that has been puzzling people in statistics and machine learning, that big models can overfit data but still generalize well. There have been a lot of theories not related to algebra trying to explain that, mostly from the point of view of the landscape. The people say that even when there are a lot more parameters than the data points, so even if it overfits, the landscape is still in some way smooth. So it's not, it doesn't necessarily have sharp minimums and things like that. So most of that work has been done by analysis or statistics. But from the point of view of algebra, I'm not sure. So symmetry gives us a way to at least prove that minimum has more than one, has more than 0 dimension. So it's a curve or surface or space instead of isolated points. But for now, that's about all I know.
Well, Bo, this was a really wonderful talk. Thank you so much for coming to talk to us. I really appreciate it. If people have questions or they have ideas and they want to reach out, can they email you? What's the best way to contact you?
Yeah, sure.
Okay, sounds good. Well, cool. Thank you so much. I'll post this online. I'll let you know when it's up. And yeah, thank you again. Really appreciate it.
Thank you so much. Bye.
Okay, bye.